Okay, we've been talking about bonding here in chapter 12. And last time we talked about how to sort of draw our Lewis structures and remember our least electronegative atom is in the middle. Remember, as we talked about, we basically want to start with one bond from the center to the outside. We then want to distribute our remaining electrons as dots on the outside atoms. Then work to the center and also put those on as dots. So remember, as we talked about, we don't really want to kind of double bond, triple bond, or anything like that, kind of out of the box. We actually want to save double bonding, triple bonding for a situation where somebody has not met the octet rule. So once you get to the center atom and you distribute those electrons, and you're out of electrons, if somebody does not have 8 electrons around it, then you want to fix it by making a double bond. And you really want to sort of exhaust all your double bond opportunities there. And then if that doesn't fix it, then a triple bond should fix it. Remember, though, if we are going to, for example, something like this that we saw, if we need to make a double bond, we are going to bring a pair of electrons in to make the double bond. We can't add any more electrons, otherwise we'll have too many. We can't just make the double bond, otherwise we'll have too many electrons in the picture, and we can make our double bond. We also talked about in an opportunity like this where there are really multiple spots where you could have made that double bond. You could draw another Lewis structure, which is an equivalent structure, which is known as a resonance structure. And resonance structures are usually separated by these arrows. And the sort of simple answer to that is anywhere where there's multiple options, you can make that double bond. You could draw basically another Lewis structure that represents it. The real reason is, as we talked about, those electrons there are delocalized. And what that means is they're not really necessarily attached to this oxygen. They can kind of move around to each one. And that means at any given time, that double bond could be at any of those sort of oxygens along the way. In this case, we could actually draw a third resonance structure where we would double bonded there to the left and end up with something that looks like this. Questions on any of that there? We also talked about a few exceptions to the octet rule, which is an incomplete octet, which boron, aluminum, and beryllium are perfectly fine with less than 8. And also, there is an odd number of electrons, which means you have an unpaired electron as another exception to the octet rule. Those are sometimes referred to as free radicals. They're reactive because of that unpaired electron. And lastly, the one that you'll see the most, especially when you go to the next class, is the expanded octet. And that is once it could go greater than 8. And that again is where sulfur is on the periodic table and kind of down. The reason they're able again to do that is because they have the d orbitals available to them, because that's the third energy level where that starts. So they have places to add those extra electrons to. That, for example, something like nitrogen, oxygen, and carbon, they do not have available to them those d orbitals, so they cannot add more into them. Any questions on any of that there? All right, so continuing on here to sort of wrap up this chapter, we're going to talk about molecular geometry next, which is basically the three-dimensional arrangement of the atoms and the molecule in space. When we talk about geometry, it does help us describe sort of how the atoms and the electrons are arranged in three-dimensional space. We cannot necessarily predict it from the Lewis structure, but if we know really two important information that we can actually get from the Lewis structure, and those two important pieces of information are the number of electron pairs around the central atom And when you do geometry, it is always about the atom in the center. So it's always about the center atom and the number of bonds. So those you can sort of see from your Lewis structure. And if you know the number of electron pairs and the number of bonds there are, thank you, you will then be able to sort of predict the geometry of it. We are going to actually talk about two different types of geometry. We're going to talk about one that describes how the electrons are arranged around the central atom. That is what is sometimes referred to as the electron pair geometry. And for the rest of this sort of lecture here, I'm just going to call that EG, so I don't have to keep writing that. But that basically describes the arrangement of the electrons in three-dimensional space around the central atom. The other type of geometry is the molecular geometry. And sometimes people refer to this as the shape of the molecule. And for the rest of this, I'm just going to call that the MG here, which is molecular geometry. And in certain times, in certain cases, the electron pair geometry and the molecular geometry will be the same name and will be the same. But there are situations where there are different names, one for electron pair geometry and one for the molecular geometry. And we'll talk about why that happens in just a bit as we go through it. But there'll be two names, one electron pair geometry and one molecular geometry, or the shape. Now, the basis of this approach is the idea that ultimately, when we make bonds, are in bonding, we basically have electrons around, and electrons are negatively charged, which means electrons near electrons really, for the most part, don't want to be near each other because they both have a negative charge. And since they both have a negative charge, they were going to try their best to get away from one another. The problem, though, is that they are in a bond, are attached to this atom, so they really can't escape. But what they will essentially do is, for the most part, try to get as far away from one another as possible. And what that's going to lead to is, in some cases, different types of geometry that we see. And the difference relies upon whether or not there is for sort of non-bonding electrons present or no non-bonding electrons. And we are going to look at this, which is known as VSEPR, and that's valence shell electron pair repulsion model. And it's basically divided into two types of molecules. There are molecules where there are no lone pairs on the central atom. So if you draw your Lewis structure, there are no dots basically on your central atom. Then the other type of ones are where there are dots basically, and there are lone pairs. So yes, there's dots on the central atom. Now, probably the biggest rule to remember when you are doing geometry is everything pretty much counts as one. And what I mean by that, there's those two things that we're going to count, which is the number of electron pairs and the number of bonds. So regardless if you have non-bonding electrons, regardless if you have a single bond, a double bond, or a triple bond, it doesn't really matter when you're doing geometry. All of these things count as one electron pair and one bond. Obviously, this doesn't count as a bond, not a bond, but it does count as an electron pair. So if you have a single bond, a double bond, a triple bond, they all just count as one when you're doing geometry. And all electron pairs basically count as one as well. So everything pretty much counts as one. And that's a really important thing to remember when you're doing geometry. The second one is not super important for us, but if you can draw a resonance structure for a particular compound, you could apply this geometry to it. And in most cases, any of the resonance structures that you draw usually will have the same geometry. So for example, I drew the carbonate earlier here. All three of those pictures, if you did the geometry for all three of them, will end up being the same geometry, basically, in most cases. All right, so let's take a look at really the simplest geometry you could ever have, and that's a diatomic molecule. So a diatomic molecule, as we hopefully know, is basically a molecule that only contains two atoms. And you basically have two atoms attached to each other. In this case, there really is no central atom because there's nobody in the middle. But the only way to connect two things is basically a straight line. So the geometry is always linear. So if you have a diatomic molecule, shortest distance between 2 points is a straight line. They will just be basically opposite ends of a straight line is how their geometry is going to be, and that is linear. It doesn't matter if it is two of the same, that's linear. Doesn't matter if it's two of the same with a double bond, still linear. Doesn't matter if it's two the same with a triple bond, still linear. Doesn't matter if it's two that are not the same, still linear. So any sort of molecule that's diatomic, because there's only two atoms, there's no central atom, they only could be basically arranged opposite ends of each other in a straight line, and it will always be linear. Now, when we get to sort of three or more atoms, we have to look at those two things that we've been talking about, which is how many electron pairs there are in the central atom and how many bonds there are. So let's take a look at that. So the first example here we're going to actually look at is an incomplete octet, and this is beryllium chloride. And in this particular case, as I mentioned, it is always the center atom that you want to look at. So when you're doing geometry, that is the only atom you should ever look at is the central atom and what's happening there. Again, we want to do the number of electron pairs there are. So when we look at this, there are two electron pairs. There is one here for the bond and one here for the other bond. So that is two electron pairs in this particular molecule. And something with two electron pairs, the electron pair geometry name is linear. So what's going to happen is those electron pairs are going to try to get as far away as they can from each other, and they're going to end up on opposite sides of the center atom. That's as far away as they basically can get from one another. The number of bonds that we have here is one bond and two bonds in this case. And something with two electron pairs and two bonds, the molecular geometry, or the Mg as I'll call it, this guy's Eg, is also going to be linear. The reason the names are the same here is we have bonding electrons. So as those electrons move, the atoms are bonded to it, so they move with the electrons, and the atoms end up in the exact same location as those electrons on opposite ends of each other, and ends up with this linear geometry, which is a bond angle of 180 degrees. So 180-degree part. This is, again, as far away from each other as they could get without going too far. The next sort of example is also a incomplete octet here. And once again, we're going to look at the central atom, and we want the number of electron pairs. And number of electron pairs here is 1, 2, and 3. Something with three electron pairs is going to have an electron geometry name of trigonal planar. This is also sometimes called triangular. Now, when we look at the bonds here, one bond, two bonds, and three bonds, it has three bonds. And the molecular geometry here is going to be also trigonal planar. Now, what's happening in this case? What's happening in this case is we have an extra sort of bond and an extra pair of electrons that are present. So what happens is, unlike in the previous example, these guys have to get some distance from each other, but now these guys can't get too close from each other either, and it ends up in this trigonal planar geometry. And you could kind of see it here, why it's sometimes called triangular. It basically makes a triangle as to how they get apart from each other. And again, you can kind of see it here. Bond angle here, 120 degrees, making that triangle here. So bond angle 120. And again, because of that third sort of bond, if you will, they're not allowed to get 180 degrees from each other. They got to kind of keep distance from everybody. The next sort of geometry that you're responsible for is something like this, which is clearly messed up badly. Let me redraw that. And in this particular case, once again, we're going to go to the center atom here. And the center atom is right there. And the number of electron pairs on the center atom is 1, 2, 3, and 4 electron pairs. Again, when you're counting electron pairs, doesn't matter if they are dots, lines, whatever it may be, they all count as one. And something with 4 electron pairs will give an electron geometry name of tetrahedral. Now, when we talk about bonds, it has 1 bond, 2 bonds, 3 bonds, and 4 bonds. And the number of bonds there are going to be 4. So something with 4 bonds, the molecular geometry name is also going to be tetrahedral. So we have 3 sort of bonds, if you will, and it made like a triangle type shape. In this case, we got a similar thing sort of happening. We got our bonds over here. We got really, because we have now 4, we got all these guys got to kind of keep their distance from each other. And again, they can't get super close to one another. So they do end up in this sort of, it's sort of like a triangle here on the front of it, and this sort of tetrahedral, almost pyramidal type of shape there on the bottom. And that is tetrahedral and tetrahedral. Up until this point, when we look at these sort of examples here, both the electron geometry name and the molecular geometry name are the same. And in this case, the previous case, and so forth, they were all the same name. And the reason they were all the same name is when we draw our Lewis structures, there are no dots on the central atom. And that means the only type of electrons that we actually have here are bonding electrons. And because there are bonding electrons, that means they have an atom attached to them. So as those bonding electrons move, so do the atoms. And what ends up happening is the overall shape of the molecule ends up being the exact same shape as how the electrons are arranged there, because they're basically all moving together as they move around. Now, what happens when we start to introduce non-bonding electrons? So when we start introducing dots there around the central atom, a couple things happen. One thing that happens is we no longer have that atom there, right? Kind of in the way. We're missing an atom. It's kind of the only way we have dots. And secondly, what that also does is it gives everybody a little bit more room to spread out, because you don't have that extra atom sitting there. So it's got some extra room to spread out. And the name that it actually affects is the molecular geometry name. So once we start introducing non-bonding electrons on the central atom, the molecular geometry name will change. This name stays the same. So the electron pair geometry name will stay the same. It's just based on how many electrons you got. It doesn't really matter. But because we have some non-bonding electrons there, we will start to get some different molecular geometry name because of that extra sort of flexibility, if you will, extra movement that they can do to try to get away from each other. In addition, as we'll talk about here in a second, the types of electrons that are near each other makes a really big difference of like how far they want to try to get away from each other. So let's talk a little bit about that. When we talk about electrons, there's really 3 types of interactions that we can have. We can have bonding electrons near bonding electrons, which is basically what we've just been talking about. So on your Lewis structure, that's basically lines near lines. So if all you got are lines happening there, no dots, that's kind of the best situation in terms of electrons. That's their most sort of manageable, I'm okay with that type of situation. The next sort of best situation is when you have lone pairs near bonding electrons. So dots near lines. That's getting a little bit worse. They're not super happy to be near each other. So we're going to get a lot more movement away. And it has a little bit more movement, again, because it has basically less bonds there, and it can get those electrons away. The worst situation that you could have in terms of electrons being near each other is non-bonding electrons near non-bonding electrons, are dots near dots. Those are the worst situation that you could have. And they will try to get as far away as they can from one another. And they're able to do that because, again, they have no atoms attached to them. So they're kind of able to kind of really spread out and get away from each other. So what you have to kind of think about is, as these, for example, non-bonding electrons are moving away, everything else there are moving accordingly because they're also trying to get away from each other. So as these electrons start to move, other electrons will move. And that's what's going to give us these different sort of shapes that we see. So let's take a look at the first example of this, sulfur dioxide. And if we draw sulfur dioxide, which we, I think, did the other day, we will end up with something that looks like this, for example. And once again, when we do geometry here, again, it is all about the center atom. So it's all about the center atom. No other atom's important. Now, in certain cases, you may have more than one center atom, but in this case, we have just one. We're going to do the same thing here. The number of electron pairs in this case is 1 electron pair here, 2 electron pairs here. And remember that the double bond or triple bond or single bond counts as only 1 electron pair. So again, this would give us 3 electron pairs. As I mentioned before, the electron pair geometry name will not change. So as we saw earlier, something with 3 electron pairs is trigonal planar. Now, when we talk about bonds that it has 1 bond and 2 bonds. Again, everybody counts as 1. Now, something with 3 electron pairs and 2 bonds has a molecular geometry name of angular. Now, some people will call this bent. Some people will call this bent angular. But we're just going to go with straight up angular on this one. And what happens in this particular case is sort of this. We have a few different types of interactions happening here. We have our bonding electrons near bonding electrons, which is sort of manageable. And we also have our non-bonding electrons near bonding electrons. So what happens is these non-bonding electrons definitely want to get away from those bonding electrons. So as those non-bonding electrons sort of move up, what's going to happen to those bonding electrons is they're going to move down away from them and try to get away as far as possible. But what happens as well is we still have bonding near bonding, so they cannot get super close to each other either, because ultimately they don't want to be near each other either. So as those non-bonding electrons move up, those bonding electrons move, and since they have atoms attached to it, that is what gives us this sort of angular shape here that comes along as they're moving away from each other. And it does have a bond angle of less than 120 degrees. The bond angles are related to the electron pair geometry. So the electron pair geometry here is really where the bond angles are related to. And here's less than 120 degrees, again, because we have, unlike in our true trigonal planar where we have that guy as a bond and kind of locks into place, without that extra bond up there, again, it gives it a little bit more flexibility, and we end up with a bond angle a little less than 120 degrees. Questions on that one there. All right, so continuing on here, next sort of example is something like we see here in ammonia. And again, we're going to focus on the central atom and our number of electron pairs. Once again, 1, 2, 3, and 4 electron pairs. So remember, again, the electron pair geometry name does not change. So that's going to give us an electron pair geometry with 4, which is tetrahedral. Now, what happens in terms of bonds here? We have 1 bond, 2 bonds, and only 3 bonds. And something with 4 electron pairs and 3 bonds has a molecular geometry name of trigonal pyramid. And trigonal pyramid is the shape of it. And again, in this particular case, we have a similar sort of process happening here. We again have those non-bonding electrons, which again are going to try to get away, obviously, from our bonding electrons. The difference, though, than we had here with the previous one is we got that extra bond right about there, which also needs to kind of keep its distance from one another. And what ends up happening is as they do that, these guys trying to keep their distance as best they can, make sort of a pyramid shape on the bottom there. And again, a triangle and a pyramid together gives us our trigonal pyramid type shape. So these bonding electron guys can kind of get a little bit closer to each other because that's okay. And again, that's going to kind of keep all those distances away from each other. Again, it's not going to end up in that angular because we have that extra sort of bond in the middle that we didn't have on the previous one. Bond angle here is less than 109.5 degrees. That's like 107-ish probably or so in the NH3 sort of arrangement. Now, this is a good point to talk about, which is in this situation here with 4 electron pairs and 3 bonds. The molecular geometry name is trigonal pyramid. We just saw not too long ago number of electron pairs being 3 electron pairs, number of bonds being 3. That is trigonal planar. Yeah. These are different. So this name and this name are different, and you do need to specify which one you're talking about. You cannot just write trigonal and let me choose because I'm going to choose wrong because I did not pass this class. So I'm going to pick the wrong one and put an X. So make sure you don't just write trigonal. You got to commit to trigonal planar or trigonal pyramid as they do represent different things. You can't just write trigonal. Or my other favorite, trigonal, I'm very confident with the P, and then maybe not so confident with the rest of the word there. And like, oh yeah, that's clearly planar. Can't you see it? Or pyramid, or which one was it supposed to be? Yeah, so you got to commit to one or the other, but they are different. They do represent different geometries, and they do represent different bond angles and stuff like that. So don't just write trigonal for those guys. All right, the last. Not sure where that slide went, but hey, we'll go back this way and we'll just do it here. The last geometry that you're responsible for, it kind of disappeared. All right. The last geometry that you're responsible for is something like water, for example. And if we look at something like water and we draw water, it looks something like this. And if we look at water here, once again, we're going to focus in on that center atom and the number of electron pairs. We have 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. Once again, does not matter lines or dots. Number of bonds in this case, 1 bond and only 2 bonds in this case. So just like we saw a second ago, our electron geometry is based on 4 electron pairs. So that is tetrahedral. Now our molecular geometry, because it only has 2 bonds, will actually end up with a geometry known as bent or V-shaped. And this is why, for example, that we will be using angular for that previous one, because this is really bent or V-shaped. And what happens in this situation is very similar. We end up with our non-bonding electrons, which basically is the worst sort of interaction you could have. So they like, I'm going to go this way, I'm going to go this way, and try to get as far away as possible from each other. Again, these guys also need to get away, and these guys can't get too close. So what ends up happening is we end up with this kind of bent or V-shaped structure here that we end up for water. Bond angle here is less than 109.5 degrees. Now, these are the geometries that you are responsible for. You have a table in your book similar to these tables here. Actually, similar to this one, I'm pretty sure. And again, that's our electron pair arrangement, which you do need to know. And our molecular structure, which you do need to know as well. And I think the only one missing off of here is our uh, th three electron pairs and two bonds, which would give us our trigonal, planar, and our angular. Yeah. So you do need to know those guys along the way. Now, should I do it this way? What happens if you do have a molecule, for example, where there is more than one central atom? Although I don't think too much in this class, you'll come across that, but just for future reference as well, or maybe you will come across it in a homework problem or something like that. So let's just say, for example, I drew a Lewis structure. It looks like this, a little organic guy, a little methanol, right? And when we look at something like this, we essentially do have more than one central atom. So in this particular case, that's a central atom, and that is also a central atom. So essentially what we do in this situation is we do the geometry for each one separately. And although I can't really necessarily do it here on the screen, but what we would essentially do is if we were looking at the carbon, we would essentially just kind of put our hand over that side of the molecule and not even worry about it. The only thing that we would worry about when we're doing the geometry in a situation like this is this bond would still count for the carbon as well. So kind of put our hand over that side and then look at. So now when we look at the carbon, it makes it pretty simple. When we look at this carbon here, the number of electron pairs is 4. It has 1, 2, 3, and 4. And that means its electron geometry is tetrahedral. And the number of bonds would be 1, 2, 3, and 4. And that means its molecular geometry would also be, in this case, tetrahedral. So remember again, as we talked about, if you have no dots on the central atom, basically both the electron pair geometry name and the molecular geometry name will be the exact same name. So no dots, they're going to be exactly the same name. Now, once we did that, what we will essentially do is move our hand from over here, and now we will essentially just put our hand and cover up the other side of the molecule here. So we'll just kind of go that way. And now we can look at the oxygen. And once again, though, that bond that kind of connects where we put our hand, this bond is still going to count for the oxygen as well. So when we look at the oxygen here, the number of electron pairs is going to be 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. So its electron geometry is also going to be tetrahedral. But in terms of bonds, in this case, we have 1 bond and 2 bonds. And something with 4 electron pairs and 2 bonds, the molecular geometry shaped is bent or V-shaped. So really, this molecule kind of looks like you have this sort of tetrahedral part on this, and then you have this kind of bent or V-shaped on that side of the molecule. So it has two different sort of geometries that occur here. So if you have, again, something that has more than one central atom, you basically could just do the geometries for each one individually, put your hand over the other part of the molecule that you're not looking at, but you do still need to count the bond that's attaching the other side. Any questions on that there, or geometry? I would say that probably the best way to do it in geometry is unfortunately memorization. Most people can't visualize three-dimensional in their head. So there's this table, which is a really good one. There's also one up on Canvas that I made, sort of this table that'll help you with number of electron pairs and number of bonds. That is a good way to just memorize the names that go with it. The last thing we're going to talk about in this particular chapter is molecular polarity. And molecular polarity is whether or not the molecule as a whole is polar or nonpolar. So earlier in this chapter, we talked about bond polarity, and bond polarity is where we use the difference in electronegativity values to indicate whether or not that bond is polar, which means the electrons are not shared equally, or if it is nonpolar, which means the electrons are shared equally. When we talk about molecular polarity, we're not necessarily talking about the individual bonds, but we're talking about everything as a whole. So all the bonds that are in that molecule, is the entire molecule sharing those electrons equally? And if it is, it would be a nonpolar molecule. And if it is not sharing them equally, it will be a polar molecule. Only polar molecules have what are referred to as dipole moments. Dipole moments is represented with that same arrow that we used previously with our polar bonds. And in this particular case, it points to the more negative side of the molecule. And again, the back part here is the more positive side of the molecule. And only, as I mentioned a second ago, only polar molecules have dipole moments. So polar molecules, in a sense, have a positive side and a negative side to their molecule. And that's really important for how molecules can interact with other molecules. Nonpolar molecules do not have dipole moments. They are essentially neutral molecules. There is no negative side to that molecule. There's no positive side to that molecule. You basically have overall equal distribution of those electrons, so you don't get any type of charge. So polar molecules and nonpolar molecules are very similar to how we think about polar bonds and nonpolar bonds. Polar bonds has a positive and negative side. Nonpolar bonds is a neutral. There is no positive or negative side. Same thing with the molecule as well. They are different though in all cases except for one situation where bond polarity, where you use the difference in electronegativity to figure out between these two atoms, is that a polar bond or not? And molecular polarity will be the same. And the one place where that occurs is with diatomic molecules. And diatomic molecules are probably the simplest and easiest ones to figure out whether or not the molecule itself is polar or nonpolar. The reason for that is you have in a diatomic molecule just two atoms. And because you have two atoms, they are connected by only one bond, right? And that is basically the entire molecule. There's nothing more to that molecule other than that. And what that means is, in this case, if that bond is polar, the molecule will be polar. And if that bond is nonpolar, the molecule will also be nonpolar. And that's because it is the only bond present. So, for example, if you have a homonuclear molecule like H2, when we look at H2, this is the only bond present. That is a bond between two hydrogens, which if you look up the electronegativity values are 2.1 and 2.1, which obviously gives you an electronegativity value of 0. And remember, 0 to 0.4 is a nonpolar bond. And that means obviously here, this is a nonpolar bond. And really, you don't even need the numbers, by the way, to hopefully recognize that. And because that is the only bond in the entire molecule, that would also be a nonpolar molecule. Once again, it doesn't matter if it's single bonded, double bonded, or triple bonded. If you did the oxygen here, this would also give you a difference in electronegativity of 0, and that would be a nonpolar bond. And once again, this is the only bond that is present in that molecule, and that would make it a nonpolar molecule. Now, if I had something like HCl, this bond between hydrogen and chlorine is a polar bond. And because, again, this is the only bond that we see in this molecule, this would also make this a polar molecule, where our dipole moment will go in this direction, heading towards the more negative side of the molecule. And our, again, back part here by our hydrogen would be the more positive side of the molecule. So this would possess a dipole moment heading in the same direction towards the chlorine because it is really more electronegative. So diatomic molecules, super easy to figure out polar or nonpolar for the molecule. It is because they have one bond, and if that bond is nonpolar, it will be a nonpolar molecule. And if it is polar, it will be a polar molecule. Any questions on that one there? Now, if everything was that simple, that would be great, but it's not. So when you get to 3 or more atoms that are involved, so when you have 3 or more atoms, you have to look really at 2 things. So you have to look at, are there polar bonds? And you do have to look at its geometry. And the geometry we're referring to in this case is actually the molecular geometry, or its shape. Now, let's just take a classic example here, which is CO2. And if I draw CO2, looks something like this. We draw our Lewis structure. And the first thing that we want to determine here in CO2 is there polar bonds? And the answer is yes, because carbon, nitrogen, oxygen, fluorine, they're in the same row. Oxygen is further to the right, which makes it more electronegative. And we would have a polar bond heading towards basically the oxygens in this case. So this is, yes, we do definitely have polar bonds here. So since we have polar bonds in this molecule, you may say to yourself, it's probably going to be a polar molecule because that sort of makes sense. It has polar bonds. Seems like it's going good. But because this is three or more atoms, we do have to also look at the molecular geometry here. And if we look at the molecular geometry here, the number of electron pairs on the carbon is 1 electron pair, 2 electron pairs. And the number of bonds here is 1 bond and 2 bonds. And that's going to give us a molecular geometry and also an electron pair geometry of linear. It basically is going to be a straight line. So what happens in this particular case is we basically have CO2, which is like my pen here, straight line. And on one side of my molecule, I have oxygen pulling this way. On the other side of my molecule, I have oxygen pulling the other way. And I'm actually pulling in opposite directions here. Is my pen going anywhere? My pen is not moving, right? And because of this geometry, they're actually canceling each other out. So even though it does contain polar bonds, because of its molecular geometry, this is actually a nonpolar molecule. You could think of polarity kind of like tug of war on a rope, right? If you're playing tug of war, right? You got a little flag in the middle, people pulling on the rope. And in a case where everybody is pulling on the rope equally, nobody's moving, right? It's just going to kind of stay in the same spot. And also where things are being pushed together, right? So you can think of like a swinging door. If somebody's on one side of the door and there's somebody's on the other side, they're pushing equally, right? The door's never going to open, right? So it's just going to kind of stay there. So there are certain cases where polar bonds will cancel each other out, and it always occurs when they're sort of equal and opposite of each other, either pulling or pushing against each other. So this is a really good example to demonstrate that you definitely can have a molecule that has polar bonds, but because of its geometry, it actually can end up being nonpolar overall. So if we look at something like water, which we saw earlier as well, and we go this way. We want to look to see if it does have polar bonds, and in case of this, it does have polar bonds heading towards the oxygen in this case, as it's being more electronegative. So it does have polar bonds just like the other. But now when we look at our geometry here against our oxygen, our number of electron pairs, as we saw in that last one, is 4. And our number of bonds here is 2. And that's going to give us a geometry of bent or V-shaped. Now, in this particular case, the geometry we have is no longer a straight line. We basically have almost like this kind of V, and we got sort of electron density heading towards the top where they're kind of meeting. And you could think if you had like a rope towards the top of this and you just kind of pulled right up, the whole thing would kind of move. And in this case, they actually will add to each other, and those bonds that are polar will result in what is referred to as a net dipole moment happening in this direction, where the oxygen of water side, or the oxygen side of water, is more negative. The hydrogen side of water is more positive because of this, and this would be a polar molecule. Now, this happens because these bond dipole arrows, they are vectors, I believe, right? And that's what they call them there in physics, I think. They have direction, they have magnitude, I think, and I fell asleep, I think. And then I woke up and I remember them saying again, in certain cases, they do cancel each other out like we are talking about, but in some cases, they actually can add to each other. And in this case over here with water, you got like a little vector going that way, you got a little vector going that way, and maybe they combine to head in that direction, and you end up with a net dipole moment that's happening because they do add to each other. Now, the size of the dipole moment can be different. You could have a big dipole moment, you could have a small dipole moment. You could actually calculate it, which we won't do in this class. But not all dipole moments are super big separation of charge. Some are a little bit smaller, sort of separation of charge and stuff like that. But clearly, this is chemistry, and nobody wants to do vectors. Otherwise, we'd be in physics right about now, I imagine. So there must be an easier way to figure out molecular polarity than drawing vectors all over the place. And there really is, and you'll probably get the answer right, I would say 99% of the time. So there are some geometries that are symmetrical geometries. And the geometries we're talking about here are the molecular geometries. And for you guys, your symmetrical geometries is trigonal planar and tetrahedral. And what each of these geometries have in common is when you draw your Lewis structure, there are no dots, or lone pairs, on the central atom. So if you draw a Lewis structure and you end up with the central atom that has no dots on it, and you have no dots and all the outside atoms are the same, it is a pretty safe bet to call that thing a nonpolar molecule. So for example, if I take carbon and I attach some fluorines there to it, It does have polar bonds heading towards the fluorine, but I don't really have to work too much about it. I could just go to the central atom, go, I see no dots. I see everybody on the outside is the same atom and element. This is going to be a nonpolar molecule. Again, because what's going to happen is basically each of those fluorines are going to end up in a corner of the tetrahedral. So again, go back to the rope example. You got everybody equal and opposite of each other pulling on the rope, and they're all just going to cancel each other out, right? So we got 4 people and a rope kind of attached to each other, and everybody kind of pulls equal and opposite. The rope is not going to go anywhere. They're going to cancel each other out. Now, the exception to this is if I take this exact same sort of guy here, and instead of having 4 fluorines attached, I swap out one of those guys, say, for a hydrogen. Now, I still have polar bonds heading in these directions, right? But the carbon-hydrogen bond is actually nonpolar in this case, right? So what I essentially have in this case is all 3 of these guys pulling on the rope, right? And this guy over here not pulling so much in the other direction, right? In fact, he's actually slightly going with them because carbon is more electronegative. So you can imagine if 3 people kind of pull the rope and one's just kind of hanging on, not really pulling, the whole thing's going to kind of move. And now instead of being nonpolar, because all the outside atoms are not the same, this will now become a polar molecule. So if you draw a Lewis structure, no dots on the central atom, everybody on the outside is the same element, pretty safe bet to go nonpolar molecule on it. If you draw a Lewis structure, no dots on the central atom, but everybody on the outside is not the same element, pretty safe bet to go polar molecule on that. You're going to have some type of unequal distribution of it. Now, there's also some unsymmetrical geometries. And for you guys, that would include angular, trigonal pyramid, and bent or V-shaped. And what each of these sort of have in common is if you draw your Lewis structure, you will have dots on your central atom. And if all the outside atoms are the same, then it's a pretty safe bet that that's going to be a polar molecule. So we could take water, for example, that we saw earlier. Really, if you go to water, all you have to go is go, I got dots, I got everybody the same. That's going to be a polar molecule. Yeah. So you literally can do molecular polarity super quick, and you'll probably get them right almost all the time by going dots or no dots. So again, no dots, everybody the same, non-polar. No dots, everybody on the outside not the same, polar. Dots, pretty safe bet, polar, and everybody's on the outside the same. Even in a lot of cases, everybody on the outside is not the same. Also, a lot of times it will be polar as well in a lot of cases. So it's a pretty safe bet. You got those kind of polar guys who will have those dots. What that leaves you in terms of having to maybe figure out is only linear, which is a straight line. So you could kind of do the rope example for that. If they're pulling in opposite directions, they will cancel out. If they're like pushing in the same direction, they'll cancel out. But it is possible for linear that you can, for example, have something that is all heading in the same direction. If that was a linear geometry, then again, it would be like somebody just on one side of the rope pulling and the whole thing would move, and that would end up being polar. So this would be a polar situation. And again, like we saw earlier, if they're heading in opposite situations, non-polar. And also, again, if they are heading towards each other in a linear situation, also going to be nonpolar. So that's the only one you would have to sort of really worry about, and it's pretty straightforward. Any questions on molecular polarity? Yeah. Say it one more time. If the It does depend on what's attached. So that's the other component of it. So you will have the same electron pairs and same bonds will give you a symmetrical geometry, but it is important what's attached. So for example, like that one where I did the carbon with the 4 fluorines, that was nonpolar because everything was the same. But if you took one of those out, they still have the same electron pairs, the same bonds, but now they don't have the different things attached. So it has a lot to do molecular polarity, what's attached in that situation, and it could go from being like nonpolar to polar if you don't have the same stuff attached in that case. Yeah. Other questions? But for the one with the dots, it's almost a safe bet in most cases. That's going to probably lead you to a polar molecular polarity when you do have dots. So if we take a look at some of the ones that we maybe have drawn along the way here, so we got something like this. Something like this, I think we saw there. Um, this. Uh, uh, let's read this one there. Let's do. Uh, we'll do. We did that one right. All right, so let's take a look here. So actually, let me do one more here. Actually, I'll just do this one, I think. All right, so let's take a look, and we want to do, is it a polar or non-polar molecule? Yeah, so why don't you take a second there, and for each of them, decide what you think they are, and then we'll go through them. Here, so I'm gonna do the dots, no dots for most of them. Then I have 3 or more, so I'm gonna go here. I look at it, I see no dots. I see all the atoms on the outside are the same element. That should be polar or non-polar. That should be non-polar. It's going to be one of those symmetrical situations. I come here, I look at the central atom, I see dots, I see everybody on the outside is the same. That's going to tell me this thing is polar. Yeah. I come here, I see dots, I see everybody on the outside is the same. That's going to tell me it is polar. Yeah. I come here, I see no dots. Are all the outside atoms the same element? They are not. So when they're not the same element, it is going to be polar, yeah, in this case. I come here, that's only 2 atoms, which means at this point I just need to think about the bond that I see since there's only one bond present. And that one bond's between 2 nitrogens, which I know should share the electrons equally and make a nonpolar bond, which means that this molecule would be nonpolar because of that. It's a diatomic molecule. I come over here, I again see a diatomic molecule, so all I have to look at is the bond. And that bond there is a polar bond between hydrogen and fluorine with an electronegativity difference of 1.9. And it will have a dipole moment heading in that direction, and this would be polar. Here, this guy is 3 or more. I do have to be careful on this one because this one is linear geometry. Yeah, so again, it is not a one of those symmetrical or unsymmetrical sort of situations. Here, we do not have a polar bond here. This is a non-polar bond on this side, but we do have a polar bond over here as nitrogen is more electronegative than uh, carbon. That means we have a straight line in this case where one person on one side is pulling the rope, right? It's going to move, and it would make it a polar molecule, where this would be the dipole moment heading in that direction. That would be the dipole moment heading in that direction. The dipole moment for NH3 would be heading towards the nitrogen. This is more electronegative. The dipole moment here would be heading towards the oxygen, which is more electronegative and really where the electron's going to be hanging out on that side. And also between sulfur and oxygen, the dipole moment would actually be heading towards the angular oxygens on the bottom. Any questions on molecular polarity? That really is as quick as you could do it, kind of like dots or no dots, and you you'll pretty much be correct in all answers that you give. Any questions on that there? Yeah. Okay. That wraps up, I think, this chapter, if I'm not mistaken. All right, so we're gonna go off to the next chapter for a couple minutes here that we got, which is we're gonna go not there actually. We're gonna go there. All right, so we're gonna go chapter 5, and chapter 5 is about naming. So we're gonna officially talk about how to name everything, which is nomenclature. And we're going to talk about the two types of bonds we sort of were talking about in our bonding chapter. We're going to talk about ionic compounds, which is a metal and a non-metal. And as we talked about in bonding, we're going to get, again, a transfer of electrons. And that's going to create a cation that is positively charged for our metal and an anion that is negatively charged there for our non-metal. And remember, as we talked about, there is no sharing of electrons here. The other type of name we're going to talk about is involving covalently bonded things that are sometimes referred to as being molecular. And that's between two nonmetals. And as we talked about in bonding, obviously, that's going to be some type of sharing of electrons. Again, maybe equal sharing, maybe unequal sharing, but some aspect of sharing that's going to occur. All right, so let's talk about how we sort of go between these things. When we name things, there are certain things that just go by, for example, common names, and H2O is one of them. When you see H2O, it should be water pretty much in all cases. Is not a trick question. Don't write any funky name for it or anything like that. It is not dihydrogen monoxide because nobody wants a refreshing glass of dihydrogen monoxide, right? They would rather have a glass of water. NH3 is ammonia, and CH4 is actually the simplest organic molecule you could have, which is methane in this case. So those three definitely should go by really the common names here. So when we talk about naming compounds, as I mentioned a second ago, it's really going to be either an ionic compound or a molecular compound. And again, our ionic is our metal and non-metal, our covalent, our molecular compound. It is different how we name it. We touched upon, I think, in an earlier chapter, a little bit about naming them, but it is different between ionic and molecular compounds of how you name it. So the first thing that we want to think about as well is just to back up before we get there, right? We'll go here. A reminder that when we look at the periodic table, wonderfully drawn here. There are certain things on the periodic table that have fixed charges. So everybody in group 1, when it does make a charge, will be +1. Everybody in group 2, when it does make a charge, will be +2. When we come down to group 3, for the most part, it's aluminum we're usually talking about there, is going to be +3. That's boron. And right around there is where we have that staircase that kind of comes down. And to the upper right of the staircase where our nonmetals are, starting in group 5, that's -3. Group 6 is -2 charge, and group 7 is -1. And again, these are the nonmetals. So as we talked about, metals typically will lose electrons, become positively charged. nonmetals, again, will be negatively charged. So it's kind of like +1, +2, +3, skip, go backwards, -3, -2, -1. Now, in the transition metal region, which is here, they can have a variable positive charge, these metals, because they are metals. By the way, in addition to that, underneath the staircase over here, where we have things like lead and tin and all those guys, those are technically not transition metals, but they also are metals underneath the staircase, and they also have a variable charge. And that's really important in terms of positive charge, in terms of how we name things and do nomenclature. There are 3 exceptions in the transition metal region that, although they are transition metals, they actually do not make a variable charge. And the 3 exceptions are towards the top right of the transition metal: zinc and cadmium. And then if you hang a left there at cadmium, you'll get to silver. So these 3 elements, although they are transition metals, they have a fixed positive charge. And in the case of zinc and cadmium, that positive charge is +2 for each of them. And for the case of silver, it is +1. So that is your 3 sort of exceptions in the transition metal region. Even though they are transition metals, they will make kind of fixed positive charges. So whether or not something has a fixed positive charge or a variable positive charge plays an important role in terms of how we name these sort of compounds. And for that, we will continue on later with. Yeah, so we'll lay it up there for now.